the answers up on the board as and kind of walk through the 2 or 3 questions that I had some issues or some people had issues with. So if you could pause your conversations. I've accidentally spoken 2 things at once. There it is. Okay. So I'm going to take about 5 minutes here, simply because I think I understand where your gaps are. So I'm going to try to address those first, okay? So first off, when you have a reaction, and you're like, oh, like number 2, for example. Let me scroll down to number 2 first. It says magnesium, or how much magnesium was needed to precipitate all the silver out of silver nitrate. That is a single replacement reaction. So you can address it as a single replacement reaction. So automatically you know that magnesium is solid, and the silver being very low on the activity series, magnesium is more active on the activity series. It replaces silver because it wants to bond. Well, when it bonds to nitrate, it does make Mn2+. And the silver gets booted out from its 1+ to form a solid. So I kind of just predicted the products first, and then I said, I can do this as a single replacement reaction and I'll have to do my NIE, or I can actually address it as the 2 separate half reactions that all redox reactions have. First one in this case is oxidized, second one is reduced. Balance your half reactions, multiply by 2. You could have done this just simply by inspection though, right? By just balancing, because you can balance 2 electrons and 2 atoms, and there's no complexities of oxygens and hydrogens and waters and acids. That's a balance by inspection one if you want, but I'm giving you this tool using the half reactions to address every redox reaction if that's how you need to do it. So something like this is very simple. Starting off with your stoichiometry, beginning to end. I don't think I need to review this one necessarily. But something like 3 was the, no, hold on, give me a second. 4, nope, sorry. Someone just asked me about 5. Was it 5? Yeah. How to balance it, and then how to address the stoichiometry. So the samples that you had yesterday in your lecture video, which I thought were pretty clear, there were some good explanations that I could try to keep embedded there. If they give you a hint, like it was making oxygen gas, so the oxygen has to be coming from the thing that had oxygen in it, which is the hydrogen peroxide in this case. H2O2 makes oxygen, and then if it says in acid, or it says sulfuric acid is added to it, that is not the reactant at all. Do not include that as the reactant. It is simply there to acidify the solution. And why do we need acids at all? Because we started at the very, very beginning of this whole unit with this concept. Why do we need the acids? What are they serving as? Catalysts, right? They're helping catalyze the reaction. They're acidifying the solution to force some sort of reaction to occur. And they kind of are catalysts, but not in the traditional sense of catalysts, because sometimes they are consumed, like a small portion of them, so normally catalysts are not consumed in a reaction. Regardless though, once you take your hydrogen peroxide, you form your oxygen gas, you balance with your H+ as your acid. Same thing, permanganate, we've probably written now like 20 times this exact half reaction. 5 and 2 is your balancing act of your electrons. As you go down, the titration involved 17.6 milliliters of permanganate, the permanganate solution, and what some of you guys might be doing, and I actually prefer this. This is an old answer key. I've usually rescan, but I didn't rescan because I was absent yesterday. The 0.2 millimoles of KMnO4 is truly what that is, and so I would expect maybe a 1-to-1 ratio between potassium permanganate and permanganate ion before you implement this. But the true story is really right here. You know that there's a ratio of 5 to 2. It's like a 1, but that's a 2 for permanganate, and then finalizing with your molar mass. Avery, did you get this? Is that where it is?
Yeah.
So the molar mass of hydrogen peroxide being 34. And I went with millis all the way. If you want to go from milliliters to liters, you can use moles and grams. That's fine. But I did 299 milligrams of hydrogen peroxide is what would be present in that original solution. That was neutralized, and I used neutralized very loosely here, reacted completely with the permanganate species and the potassium permanganate sample that was being titrated. And then today's lab is very similar to this, where you have some data, and the data allows you to get to this component of a larger specimen, right? So we found the actual hydrogen peroxide in a solution of hydrogen peroxide. What's the rest of the solution made of? You can do it. Hydrogen peroxide, thank you, water. So most things are aqueous solutions, and water is the remaining part. That's why not the entire sample is truly 100% hydrogen peroxide. So the last part said, from my original sample, how much was truly hydrogen peroxide. So it took the 299, that should be a 9 right there, 0.299 grams actual hydrogen peroxide over the total sample gives us about 3%. And that's what you buy in the grocery store. You buy 3% hydrogen peroxide. That's just a traditional example that uses a percent solution as the way to display how much is in it, but we've actually gone through the data actually to prove that's true. And that's what it's related to what you're going to be doing in your lab tomorrow. In your lab today, you have another sample. What's our sample we're working with today? You read the first part and you had to do a calculation with it. Say again? We're using brass. Is brass like really an element? No. What's it consisting of? Copper and zinc. Okay, so copper is what we're looking for, but that's within the larger sample. And it says in the lab that you have to mass out approximately 1.5 grams. I have these pre-cut for you, and what you'll do is you'll mass them first. And as you go, you'll notice that we're reacting only the copper with the nitric acid. Do you have your balanced half reactions with that? Yes? Okay, tell me what they are. Let me pull up the actual slides here. So in the lab itself, it told you copper solid to copper 2+, right? So what did you do to balance that? Okay, my board is super duper off. And I can review more stoichiometry with you guys. It's hard to when not all the class did it because it's meaningless to have you guys right now. Copper goes to copper 2+ and 2 electrons. True. So what's next? So you're saying say again? So nitrate yields nitrogen dioxide, and that's what? Give me some more characteristics. Brown poisonous gas, right? Okay, brown poisonous gas. What's next? Add water on the right, and 2 hydrogen ions, and so there's a 1+ charge over here total. There's nothing here, so 0. So 1+ needs to get down to 0. So 1 electron, and then you'll be balancing that with your coefficients or your multipliers. And then once you have your, and you notice that I give you 15.8 molar concentrated nitric acid, I'll help you get that because that's something I feel is kind of maybe not the safest thing to deal with. You guys will be figuring out you have the volume of nitric acid to be reacting. So today's lab is very easy. It doesn't take much work. So I'm going to go ahead and give you partially the procedure, but through like an introductory PowerPoint. And as we go through that, think about what we did in the past with Beer's Law. So what you want to do is jot down some notes about this, and I'll also show you where this PowerPoint is found on my website. Okay, so let's go ahead and move back to this. So I'm going to cut the lights in a little bit because you guys are going to talk to me. So explanation-based continuity. Okay, so we briefly learned about absorption versus transmission of light. We learned about colors, we learned about stoichiometry, we learned about Beer's Law. So keep all that in mind as we're going through this. So you guys are going to be taking your sample of brass, and you're determining the either mass of copper, which is the very, very first thing, and then the mass percent of copper, which is kind of the final question. So at these graphs you're going to see, I want you guys to tell me what, at these graphs you're going to see, I want you to tell me what they mean, and then how can they apply to our lab today. So we're going to talk about the graphs here in a second. So you have this graph here. Can you see this okay? Can you see that those data points right there? Yeah? Okay. So compare, when I have like about 3 or 4 different plots you can look at. Compare different plots or the spectra, as they're called, absorption spectra, for these different salts. And then what we're going to be doing is looking to see if the metal ion or the polyatomic ion, or both, is actually affecting this absorption. So, instead of me lecturing on this, do me a favor, everybody get a laptop. Because you can't see the graphs very well up here. Get a laptop. And then we're going to spend about 10 minutes with this before we move back to that. If you want to share your laptop, that's fine, but I don't laptop in front of you. Go to my website, and I'll start with the beginning of this while the laptops are pulling up. She had you guys grab one right when we walked in. So while the lights are pulling up, I'll do the first part, but I think it's helpful for you to have a conversation. and it says like lab for today under homework, and that's what you'll see when it pulls up. So while they are booting up, I'm going to continue up here. So just get logged in for me. My throat's really dry, so I'm trying not to stress out. Usually get laryngitis like once a year, so I'm trying not to let that be this like now. Okay, so you can kind of see this graph here. This is copper 2 nitrate here. Can you tell where the peak absorption is? Noticing that absorption is over here on the y-axis, wavelength is over here on the x-axis, and there's a little curve. Where is it peak? Say again? 650 what? Nanometers. What color light is that? And I'll give you a hint. No. Close. No. So 400 nanometers is purple. 700 is red.
Yellow.
Okay, how about ready orange? Ready orange. Okay, so that's going to be red-orange light that it's absorbing the most. We said blue at first, right? What color is copper 2? Copper 2 is blue. Copper 2 is blue. It rhymes, okay? If you don't know that, write that down. So if copper 2 is blue, is it absorbing blue light? No, it's reflecting it, right? That's the way you can see it. It reflects off the surface, and it shows you that beautiful blue color. It's not absorbing it, because if it was absorbing it, it wouldn't be blue. So that makes sense it's not absorbing blue. All right, so this one, oh, I had it bigger right here. Copper 2 nitrate. You can definitely see the same, the copper 2 nitrate, here it is right here, about 650, 700-ish. Look at copper 2 sulfate. What do you see? Sean, get logged in, man. What do you say? What do you see for copper 2 sulfate? Where's the peak absorption? Okay, is that similar to the first one? It's similar though. Is it similar? Okay, great. Next one. Where's the peak absorption? This is zinc nitrate. Basically no absorption. What color is zinc? Zinc ion, zinc 2. Say again? It's actually clear. It's a whitish clear. So zinc 2 plus, has a clear solution. So do you expect it to absorb anything? No. Do you expect it to reflect anything? No, really. It's actually transmitting 100% of the light through it. It's not absorbing anything. Yeah.
On the last graph.
Yeah.
Like where when it goes up, like on the points where it's low, would that be the color that it is that you see?
Approximately, yes. So down here, this is a good point. So I'll go back to both these. 400 to 500 is where the absorption is really, really poor. So if it's not absorbing the light, what's it doing? Reflecting it. So it's probably, the color of this species is this color-ish. But then the peak absorption should be opposite on the color wheel, which is red in this case, reddish orange. And you see that commonality between both of these copper solutions. And that should make sense. Then you see the zinc and you see nothing, right? So you're still getting my website, by the way, okay? What do you see for the iron? Where's the peak absorption? This is iron 3 nitrate. Okay, so the peak absorption is around 400, which is what color of light? Violet, okay? So violet is over here at the 400, 700 is red, okay? So yeah, it's absorbing great, the violet light, the blue light, but what's it reflecting? What wavelength? Around 600, which is where the absorption is very low, and that's assumed to be about what color? Give me an assumption here. Yellow-orange. In iron solution, iron 3 is a yellow-orange color. So that's a good observation, Levi. Okay, so with this, what is doing the absorbing? Is it the cation or the anion? The cation, the transition metal, that's the cation, the metal ion itself. So that's really what we're focusing on, and I know that you probably knew that, but I just wanted to show you by proof of concept from data, from a graph, how you can also determine that, because the common denominator between this graph 1 and graph 2, what's the common denominator here? Copper, thank you. Copper is the only thing that's common between these, and the graphs are very similar, so hence copper is the one that's controlling the absorption of these graphs. Okay, so when we do our lab today, and what we're doing is we're using copper. and we're using a spectrophotometer, we're actually going to use colorimeters, which are the Lager Pro ones. We're not going to use the big, huge machines. Remember those ones that we used last time? Using the cuvettes and the Spec 20s. We're not going to use the huge machines today. We're going to use colorimeters. So we're going to learn how to do it the same way with different equipment. We are going to be setting our settings to absorb light for copper at what setting? Where does copper absorb the most light? Okay, so someplace between 600 and 700 likely. So 650 is a great number. Write that down because you're going to forget that's where you're setting your colorimeter. And the reason we're doing that is because that's going to give us the best results. Okay? All right, so why do we need a particular wavelength? I kind of just told you this. Why do we need this wavelength? This wavelength that we're setting our specs to. Well, why can't I just use any wavelength I want? Okay, so we need to have the highest amount of absorbance to get good data. So we need to measure the absorbance, but we need the best wavelength to do that, and that's why we are choosing this very specifically. Normally, I would have you run through every wavelength and see where the best one is, and we're going to see the peaks, but I've done that for you. That's why I have the graphs up front. So I did the first half for you guys, okay? So this concept does relate to Beer's laws. Raise your hand if you're on my website and you're on this slide with me now. Awesome. Okay, so you guys can see this. So I'm going to let you guys read through the Beer's law information, but we will be using cuvettes again today. We are now at this point, we're relating absorbance, which is the big A, to C, which is concentration. So as you do that, the way we're going to do that is using our Spec 20s or our colorimeters. Colorimeters are the just the more technical Lager Pro based ones. Okay, so according to this other graph, and this is the one from Lager Pro. Actually, I did this first part. You're going to see also proof of concept again. The highest peak of absorption for copper 2 from the copper 2 nitrate solution is over here at like the 650, 700 range. These numbers are really blurry. 650, 700 though. So again, that's just you seeing that. What you're going to do first in your lab, and I'm going to tell you this point by point, and I have at the very end as well. But what you're going to do first is you're going to use a solution of 0.5 molar copper 2, it's either copper 2 nitrate or copper 2 sulfate, but it's copper 2. You're going to use a 0.5 molar solution. You're going to make 5 dilutions. Those 5 dilutions are going to be what you measure the absorbance of. So what you're going to do is you're going to make your own calibration curve. This is the very first step. So one person will be working on that. This calibration curve is important because if not, if you don't have a calibration curve, you can't determine anything that has an unknown concentration. So as you go, let's say you take your 0.5 molar, you're like, that's my first one, that's the original. You pop it in the spec, you figure out the absorbance, you plot it, number 1, high concentration, high absorbance, right? And then you do 4 dilutions on top of that, and as you go, you get 4 more data points. Those 5 data points will make a very, very good linear direct correlation. That is your y is equals mx plus b. Do you remember doing this a little bit? Okay, that's your y is equal to mx plus b. As you do that now, then someone else, you guys are going to also have someone working on the second part of the lab, which is the brass sample reacting with the nitric acid. And someone is going to be doing that because it's going to take a little while for it to react. So you guys are going to read through this as well. Those are some information pieces that's not necessarily important for me to go over right now, but you do need to know them. So we've done this, we looked at graphs, we discussed Beers to an extent. You guys have the labs in front of you. We're going to create a calibration curve. Step 1, do make sure you blank it, right? Blank, meaning it reads the 0% absorbance. Yes, okay. Someone's going to be diluting 5 good samples to get some dilutions for your calibration curve. Someone else is going to be working on that nitric acid brass reaction to get the copper out of the brass into a solution form. Because our job is, do we know how much copper is in that brass sample? Can you imagine what color the sample is going to be after we react it with nitric acid? Bluish, we hope, right? That's assuming copper is there. Do we know the concentration of that blue solution? No. How are we going to figure out the concentration of that blue solution? Finding the absorbance and then doing what with it? Plotting it or looking at your calibration curve and utilizing what you just created to find the unknown. Okay, so that's why these have to kind of be done correlated with each other. After you've reacted the brass, this right here, I'm going to make sure you absolutely do this. Your brass nitric acid sample needs to be diluted with about 50 milliliters of water so you have enough volume to work with. And as you do that, it's going to be best if you put it in a volumetric flask, because once you have a 100 milliliter volumetric flask, one, you have a standard amount, everybody has a standard amount of volume we're working with, and we will find the concentration of that 100 milliliters. Because concentration is molarity, right? Molarity is moles per liter. If you don't have a volume to work with, it gets very difficult to figure out what you're actually working with. So everyone's going to have a standard 100 milliliter volumetric flask to work with. After you figured out your absorbance, you're going to plot it on your calibration curve, and you'll figure out the molarity, the mass, and the mass percent. I went through that quickly. Do you know how to get started, though? You have your laptops up with yours as well. Yes? Okay, at the very end, it just tells you one more quick what you need to do for error analysis, graphing, if you need graphing for a habit. Make sure you are trying to work through your dilutions, and I'll show you a diagram I want you to do at the end, but that's not necessary right now. All right, so this is your same lab group. I didn't pull one person from a group before. Raise your hand from your group before. Oh, okay, after I give you guys your labs, I'll pull somebody because I don't group two that Jackson understand. All right, you guys have everything you need. Let's go to the back and get started, and then I'll leave you alone. Goggles and shoes, please. Goggles and shoes.